Okay, this is 8.2, transformations of logarithmic functions. So our goal is to determine the effects of the varying parameters of the graph. Y equals a log 10 k x minus d plus c. So, you know, it looks complicated, but this is the same stuff we've been dealing with all of our transformations for all the different functions. Yep.
So the log function is basically replace fx?
Yeah, you got it. Yeah. Replaces fx, x squared, x, whatever transformation we're applying to the function, right? Whatever it was before. Okay. So investigate the math. The function of log x is an example of a logarithmic function. It is the inverse of the exponential function. F at x equals 10x. So there's our exponential function. It's a review from 8.1. There's our logarithmic function. So again, crossing through 1, 0, crossing through 0, 1, and reflecting across y equals x. Okay? How does varying the parameters of the function in the form affect the graph of the parent function? So the log button on a graphing calculator represents log 10x. Graph y equals log 10x on a graphing calculator. Use the window settings. So we're going to get this graph. Consider the following functions. So if I were to graph this function, who can tell me what would happen to the graph? First of all, which graph would I be moving? This one or this one, if we're looking at this? Yeah.
The logarithmic.
Yeah, this is a silly question, just seeing if you're awake here. Yeah, the logarithmic function we're moving, right? We're inside the bracket, so what are we going to do with this function, Nicholas? Yes. How many? Which way?
2 to the right.
Yes, 2 to the right. So 2, -2 here, it's going to move 2 over to the right. So this point that was 1, 0 becomes 3, 0. So our graph looks like this now. Okay? And likewise for these other ones. This moves 4 to the right, and this moves 4 to the left. Any questions? Okay. Graph the functions in part B along with the graph of this. Compare each of these graphs with the graph of that. What was your conjecture? Summarize the transformations that are applied. So we already know this. We're gonna go the opposite direction that we see the sign here. Okay, on the x-axis. D. Examine the following functions. What's gonna happen here now? Luke, you okay?
Yeah.
What's gonna happen here?
So they're gonna move up and move down. Well, the first one's gonna move up 3, and the second one's gonna move down 4.
Right. Okay, so this moves up, and then this one would move down 4. Okay? So we're done that one. Make a conjecture about the transformations that you need to apply to y equals to graph each of the following functions. All right, so here's a little bit more interesting. What would happen here? Here's our y log x. Now I want to make, let's do this one first. Log 2. What do you think's going to happen? Yeah, Elijah.
Vertical stretch by a factor of 2.
Yeah, good. So there's going to be a vertical stretch here by a factor of 2. Excellent. Let's get a better graph of that one. Oh, they don't have a graph. Changing the value of a stretches when a is greater than 1 or compresses when a is a fraction. Okay, when a is negative, the graph is reflected in the x-axis. So the same idea. When a is negative now, this whole thing flips in the x. So exactly the same thing that we would expect. Okay, so if this was -2, like this one, this thing is going to flip this way. Okay? Any questions? I feel like this is a very big review. Okay, I. Make a conjecture about the transformation. So what's going to happen here? So just tell me here. Yeah, Elijah, this one?
Horizontal compression.
Good. So notice he took the value of 2 because it's an x, and he takes the reciprocal, and he said there's a horizontal compression of a half. Excellent. Here there would be, Jason?
Horizontal stretch of 5.
Horizontal stretch of 5. And here, Luke?
Horizontal compression of -1/2.
Okay.
1/2 and then flipped on the x-axis, y-axis.
Yes. Good. Okay. On the y. When we're here, it's on the y. When we're up here, it's on the x. Okay. Exact same idea. What transformations must be applied to graph this? You would make a vertical stretch or compression of A and a horizontal stretch or compression of K. All right, let's go through the examples quickly. Use transformations to sketch this function. State the domain and range. So there's our original function. They chose to use a table of values here, which we've seen the book do before. They took some key points. Okay, one key point we know is, of course, 1, 0. How could you get all these other key points? Sorry? Yeah, Nicholas? Or would you say it first? Oh, I thought you said calculator. Oh, yeah, just use your calculator, right? If you were using this method, you could get these points easily using your calculator, right? Okay? So they have the original points, and then they're going to make those transformations. So the first one is that there's a vertical stretch of 2, so they multiply all the y values by -2. So the y values change here from -1 to +2 because I'm multiplying by -2. So that's my vertical stretch. Next, I want to do my horizontal translation, so I'm going to add 4 units to the x value here. So they add 4 units, and then they have their new points, and they plot those points, which are here, and then they graph. Okay? Another way to do it is just using what you've known, make those changes accordingly. Okay? You can make that reflection just like you would do any transformations. And then our domain, we list them. X is greater than 4 because we've made that translation of 4 units to the right. And then our range still covers all the y values. Last example, we have a logarithmic function. It gives us all of the changes. So vertical compressed by a factor of 2/3, horizontal stretched by a factor of 4, reflected in the y-axis, horizontally translated, and vertically translated. And then it asks you to create an equation. This is even easier, right? We just take all those values and we plug them in, and we get our new equation. Okay, and then our domain and range. All right, in summary, logarithmic function of the form f at x equals a log of kx minus d to the base of 10 plus c can be graphed by applying the appropriate transformations. The transform logarithmic function, apply the stretches compressions given by parameters in k first. Oh, this is important, right? You want to do the parameters of a and k first, and then apply your vertical or horizontal translations. So that's the same thing as before. Just make sure you do the multiplying first before you do the addition and subtraction. Consider a logarithmic function of this. A gives vertical stretch compression, 1 over k gives horizontal stretch or compression, d gives horizontal, and c gives vertical translation. The vertical asymptote changes when a horizontal translation is applied. The domain of a transformed logarithmic function depends on where the vertical asymptote is located and whether the function is to the left or right of the vertical asymptote. And we know all this. The range of a transformed logarithmic function is always YER. Okay, and that's because we always have this happening. So no matter where you move it, up, down, left, or right, you're still going to cover all the y values. Okay, any questions?